Okay, today's about symmetry, and there are three different kinds of symmetry that a graph can have. All right, so here is one kind of symmetry. Okay, that is symmetry across the, well, what's the line down the middle? The x or the y-axis? So that's y-axis symmetry right there. Okay, and y-axis symmetry is called even. That's an even function. All right. Now there's another kind of symmetry. Take a wild guess what I'm going to call it. Odd. Okay, and if a function has odd symmetry, then its kind of symmetry goes like this. I'm going to actually graph some specific points so that you can see this better. X to the third is an example of odd symmetry. Okay, so if I put in 1, 1 to the third is 1. If I put in 2, 2 to the third is 8. If I put in -1, -1 to the third is -1. And if I put in -2, it would be -8. Can you see the curve that's happening here? You guys have seen this function before, right? Okay, so that function has odd symmetry. All right, and another way to say it is it has origin symmetry, because if I take this dot and I go through the origin and out the other side, there'll be a corresponding dot over there. You can do that with any point. Like I'm going to take the next clean one, which is 2, 8, right there. And if I go through the origin and I keep going and go all the way down here, boom, it's got another point on it that matches up with it. So if you ever have that situation and you're trying to see, is this odd or not? Because it can get in your head sometimes. Like, you can't tell if this one's got that odd symmetry. Take a point on it and see if there's a corresponding point like it. So notice 2, 8 turned into -2, -8. Get what I'm saying? So if I pound another point, let's say 3. 3 goes in there and makes 3 to the third, which is 3 times 3 is 9 times 3 is 27. So I put in 3, I get 27. If I graphed way up here on the graph somewhere, it would be 3, 27. Well, it would also, if it's odd, it would have to have what point on it? -3 and what? -27. All right. So -3, -27 would have to be on the graph if it had odd symmetry. All right, so that says something about the function. And when you put in a number versus the opposite of that number, you get the opposite answer. Okay, I want to show you these in terms of f of x's. And here they are. If you put in a -x, you should still get the same y. Now, I want to make sure you understand what that means. Okay, this is y-axis symmetry. That's that kind where this is the y-axis, right? That's that kind that would be like the classic y equals x squared kind of parabola. Okay? And if I put in a number like, let's be specific here on points. If I go over 2, it would be up 4, 1, 1, 0, 0. Here's some specific points that are on that graph. I'll go one more, 3 and 9. Oh, that's slightly off the page, but there and there. Okay, so there's some points officially that have y-axis symmetry. And why does it have y-axis symmetry? Because this spot right here, when I stuck in 2, I got 4. When I stuck in the opposite of it, I still got positive 4. So when you stick in the opposite of the x, you will still get the same y. Okay. Notice what this says about x-axis symmetry. X-axis symmetry, of course, is symmetry across that axis. That if you stick in x, you will get the opposite sorry, if you substitute x and negative y into the equation and simplify it, if its result is equivalent to the original equation, the graph is symmetrical about the x-axis. I'm going to clean this up for you at the end and hopefully make it something you totally understand. Trying to read through how it is officially defined. And this one is the one that's got origin symmetry. And that's where you put in the opposite of x, you will get the opposite of y. That's what that example I just gave you where we had 2, 8, and negative 2 goes in. That's the opposite of the x, and I get negative 8 out. So, if we were to take this equation and just ask, does this have any kinds of symmetry? Well, some important concepts. The x-intercepts. The x-intercepts are where, and try to fill in the sentence. The x-intercepts are where, what? Y equals 0. Good. That's really powerful to know. If you didn't hear that, I'm going to say it again. The x-intercept is where y is 0. So if I stick in y equals 0, do you get I can just put a 0 right here? And then that means this whole term just cancels. And that means that I can solve this and it'll tell me where the x-intercept is. So I'm going to divide both sides by 4. And I have x squared equals, what's 32 divided by 4? 8. And then x must equal the square root of 8. But there's actually 2 answers for this. Notice it says x squared. So there are 2 things. The absolute value of x is square root of 8. So x is square root of 8 and negative square root of 8. So I'm going to say plus and minus the square root of 8. So what just happened? I got 2 answers for this because, think about it, if I put in the square root of 8 there, it works. But if I put in negative the square root of 8 there, it also works. All right. So now, Mr. Server, what did you just figure out? I figured out that it has 2 x-intercepts. 2 x-intercepts of this graph right here are at positive square root of 8 and negative square root of 8. Whew, that's not even on the graph. I mean, they're not nice numbers. Well, square root of 8 is pretty close to the square root of 9, right? Square root of 9 would be 3. So it's a little bit less than 3. So it's like here and here. Does it look to you so far like this thing has symmetry across the y-axis? Looks to me like it does. All right, let's figure out the y-intercept of this thing. Finish this sentence. The y-intercept is where, what? X equals 0. So I'm sticking in x equals 0 and finding the y-intercept. X equals 0. 0 goes here. This is all gone. Divide by 2. Y squared equals 16. I hope you noticed from the last one there was 2 answers, right? So y equals square root of 16, which is 4, but not just 4, because square root of this technically is the absolute value of y, and therefore there's y equals 4 and there's y equals negative 4. So yes, you can put a plus and minus 4. I just want to make sure you know that's not because the square root of 16 is plus and minus 4. It's not. It's because of that absolute value little dance that I just did there. Plus and minus 4. Those are the y-intercepts. Well, here's a y-intercept at 4. Here's a y-intercept at negative 4. Now that's weird because that doesn't pass the vertical line test then. Do you get what I'm saying? Remember the vertical line test? If you have a line that goes straight up and down and hits twice, then that thing failed the vertical line test. That doesn't mean it can't exist. It just means it's not a function. All right, so, but does this look to you like it's got symmetry across the x-axis? Okay, good. It's got both kinds of symmetry. Could it possibly also have the other kind of symmetry? It's already got 2 of the kinds of symmetry. Could it have that last kind of symmetry? Like, let's say I had a point over here. Could it be that if I go through here that it would come out the other side and hit over there? Is that possible still? It is possible. Could this be like the graph of a circle or something like that? Or an oval? An ellipse? All right, so this is kind of slow to try to graph this thing. Okay, takes a while. But it is valuable for you to know how to find x-intercepts and y-intercepts, and then you can tell if they're reflecting whether or not you're getting the right kinds of symmetry. Okay, so that's helpful. Sample points. Do you get, I can put in any numbers that I want to. I can pick anything I want for x and then figure out what y has to be. Well, I already put in the zeros, so let's try sticking in something else and see what we get. Oops, I should put a dot back there. These two guys. Let's say I put in 1 for x. Then I can figure out what y has to be. See what I mean? Or I could put in 2 for x. Maybe that'll work nicer. 2 squared is 4. 4 times 4 is 16. And then if I subtract 16 from both sides, then I'll have 2y squared equals 16. Then y squared equals 8. And then y equals plus and minus the square root of 8. What did I just do? I just stuck in one value for x, which was 2. And y had 2 different answers. If I stuck in 2, I got 2 different answers. One was up here, and the other one was down here. To me, it looks like it is going to be an oval. And if it is an oval, do you get it'll have that kind of symmetry where it goes through there and hits the other side? Does that make sense to you? All right. So now, that's from a picture, but there's a much quicker way to do it. If I stick in this, a negative x and a positive y into the function. What was that rule again? If I go back here, if I stick in that into the equation and simplify, if the result's equivalent to the original, then it has y-axis symmetry. That right there is the test for y-axis sim. What do you think that one's testing for? X-axis sim. And this last one, do you remember that's the one where we had like 2, 8 turned into negative 2, negative 8? That was that origin sim. Okay, so how do we actually do it? You don't even need the picture then. If you're going to do it this last way, I know the picture helps me. I'm a visual person. When I see that something's going like this, I can be like, oh, that's got y-axis symmetry. It's easier for me to see that way. But if you have the equation, it takes a long time to graph. But if you just stick negative x and y into your equation, I'm going to stick a negative x in right here. 4, and instead of x, I put in negative x. 2 times y squared, and instead of y, what am I supposed to put in? Regular y. And I solve it. Does it look exactly like the original? Well, there's only one thing I can really do, and that's this part right there. Doesn't that come out positive? Then isn't it just 4x squared plus 2y squared equals 32? Isn't that exactly the same as the original? So that's the quick way to test if this thing has y-axis symmetry. All right, and if you're trying to tell them apart, the y-axis test has a normal y. See what I'm saying? Here's the y-axis symmetry test. You use a normal y. The x-axis symmetry test, you use a normal x and a negative y. And the origin symmetry test, you got to remember that they both get a negative. Let's do that origin symmetry test quick and just see how quick this can be. I'm going to stick in a negative x here and a negative y there. Do you get that that's going to turn back into 4x squared? And that's going to turn back into 2y squared. And it's the exact same thing as the original. And therefore, we just figured out it had origin symmetry. So that's how you tell something has x-axis symmetry, or y-axis symmetry, or origin symmetry. Yes?
So it can have two at the same time?
It can have three. Yeah. I'll give you an example of one. For example, here's one of the simplest ones of them all. It's a circle with a radius of 3. Do you get that for every point up here, there's a point reflected straight down underneath it? So do you get, okay, so let's say I pick this point. Well, then there's a point down there. It's got that kind of symmetry that's going across the x. And then it also can go this way across the y, right? So like this point goes with this point. And so it's got y-axis symmetry. And then also it's got that diagonal kind. And there's a point here that goes with a point here. So it's got all three kinds. So yeah, you can have all three kinds of symmetry at once. Is it common? No. Circles are really special and unusual, but normally you have one kind of symmetry. Most answers are going to only have one, but of course, when you're given a test in honors pre-calc, you're not going to usually use the easy normal kind. You're not going to give you a parabola and say, does it have symmetry? Because it'll be like, duh. Most people would know that. All right, so really what do you need to know? That tests for, you're going to stick that in the equation. If it comes out the same as it was, that tests for a certain kind of symmetry. What kind does that test for? Y-axis symmetry. The one that's not been messed with, it's that kind of symmetry. That's testing for y-axis symmetry. So what's the other kind? Well, that's not testing for anything. You're putting the original things back in, right? There's no such test for that. That doesn't do anything. Okay, but we could make this negative, and then it's testing for what? X-axis symmetry. Okay, and last but not least, which is what about the x and the y? Negative x and negative y. And if you stick them in your equation, and it comes out the exact same it was in the first place, then you have origin symmetry. All right, so there's x-axis symmetry, y-axis symmetry, and origin symmetry. Later on, you'll learn more about how there's some of these that are called even and odd, but that's not as important for today's homework. So, all right, let's get to the actual homework. Within your file, you will find this 1.2 day 2. And now it's got this, and it wants us to do a few points of graphing this thing. And that's not a bad review. It should know how to graph. So the x-intercept is where, what? Y equals 0. So I'm going to stick y equals 0 in here. And I'll have 0 equals x to the third minus x. Hint, if you can factor it, you should. See what I just did there? I factored out an x. Anytime you can factor something, it really helps if you do. And then, ooh, I can factor it again. If you're extra smart, you know that x squared minus 1 is x plus 1 and x minus 1. Why am I doing all of that? Because I'm solving it. I'm trying to find x. Now, that equals 0, that equals 0, and that equals 0 are my three answers. How would I have known there was going to be 3? Because if it has a 3 right there, then you're going to get 3 answers. That's the fundamental theorem of algebra, is that if there's a 3 as the biggest power it has, there's 3 answers. When things had squareds, then there's 2 answers. All right, so there's 3 answers. X equals 0, x equals negative 1, and x equals positive 1. Those 3 things are the x-intercepts. It hits at 0, negative 1, and positive 1. Now, right now, I don't know exactly what it looks like. It could look something like this, but I just know it touches those 3 spots, is all I know for sure. Then I got to find a few other things like the y-intercept. The y-intercept is where x is 0. So much easier. The y-intercept is where x is 0. I just put a 0 here and a 0 there, and then y is 0. Boom. And the y-intercept, oh, there it is. Kind of already knew that that was a y-intercept, didn't I? Okay. And then sample points. Do you get, I can put in anything. So instead of just sticking in 0 like we were for the x and the y-intercepts, I can put anything I want. So I'm going to pick things like 1. I stick in a 1, I get 1 cubed minus 1, which is 1 minus 1, which is 0. So when I put in a 1, I got a 0. Oh, I already knew that point. Dang, maybe I should put in something else. Probably 2. I put in a 2. Then I got 2 to the third minus 2. 2 to the third is 8. 8 minus 2 is 6. 2 comma 6. 2 up 6. Ooh, maybe there is something to that little wave I was doing before. Maybe it is going to be kind of like this. But I don't know until I graph a few more points. See what we're doing here? We're just picking some numbers and trying to figure out what this graph looks like. I know you're probably thinking, can I just put up in a calculator? There's a lot of these tests you won't have a calculator. And if you're ever thinking, but all the other big tests, you get a calculator. Well, the ACT you do. You get a calculator the whole time. But on the SAT, there is a no calculator section. So again, they could ask you, like, what does the graph of this equation look like? And you wouldn't have a calculator, and so just find points. And once you graph enough points, you're like, oh, it's obvious where it is. Okay, so that I put in 2, 6. I'm going to put in one more, 3. Say I put in a 3. 3 squared minus 3, that'd be 9 minus 3 is 6. So 3 comma 6. Oh, 3, sorry. 3 cubed. 27 minus 3 is 24. Okay, so I go 3 comma 24. Whoa, way off the graph. Way up there. Now, I am not going to take the time to graph all the possible points and figure out exactly where this graph is. But I'm going to put in one more over here in this zone and try to figure out, does it go down over there or up over there or what? So I'm going to put in negative 2. Negative 2 goes in. I have negative 2 to the third. Negative 2 to the third minus negative 2. And that's negative 8 plus 2 is negative 6. Negative 2, negative 6. And it does go down here. I was onto something. It does something like that. Now I kind of know how the graph looks. Now I'm looking at that graph. Does it look like it has y-axis symmetry? This point here, does there something straight across from it? No, so it doesn't have y-axis symmetry. Does it look like it has x-axis symmetry? Take this point here. Does it look like there's something straight underneath it over there? Nope, doesn't look like it has x-axis symmetry. Last kind of symmetry I can check. I bet it has that kind. Origin symmetry. Boop, 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 boop. Look at that. There's something right there. You go through the origin and it hits the other one. It has origin symmetry. Now, let's say I needed a better proof than that. Which of these 3 is the one for origin symmetry? The bottom one. So if I stuck in negative x and negative y into the original guy here, I stick in a negative y and I stick in a negative x, and I multiply it all the way out, it better look like the original. Negative y is negative x plus x. And then do you get if I multiply everything by negative 1? Oh, wait, cube, sorry. If I multiply everything by negative 1, it'll come out to y equals positive x to the third minus x. And there it is, the same as that. Moral of the story, when I stuck in this, a negative x and a negative y, I got the original equation back again, so it does have origin symmetry. Cool. I just did that problem for you, but you're still responsible for it. Like, if you weren't taking any notes on it, then I guess you got to do it at home. But, all right. So, let's look at this one. This is one of the ones you're going to have to do yourself. How are you going to figure out the x-intercept of this puppy? You're going to stick in. That's it. y equals 0. How are you going to figure out the y-intercept? You're going to stick in x equals 0. To get a few more points to kind of flesh out how the graph looks, you can stick in anything you want. Do you think I'm going to have you stick in like 12? No, you're going to be squaring it and stuff. That's crazy. Stick in anything you want for x, figure out what y comes out to be. I recommend things like 1 and 2, maybe -1, that kind of stuff, some small stuff. Stick them in, see what comes up. Then you kind of get a feeling for what the graph looks like. Let's say it starts looking like that. Does it sort of look to you like it has even symmetry? Sorry, I should say it this way. That has y-axis symmetry? Yeah. I mean, you can look at it and see that it looks like there's stuff straight across here. What if you needed to get symmetry, but you didn't have time to graph it? That's your test for what kind of symmetry? Y-axis. This is your test for what kind of symmetry? X-axis symmetry. And this is your test for what kind of symmetry? Origin. And you stick in, and then you see if it comes out to the same as the original equation. And if it does, then it's got that kind of symmetry. This is for y-axis, x-axis, and origin symmetry. All right, so you should do that one and that one. And that's it. That's your homework for tonight, those 2 questions. They got multiple parts, but any questions? All right, that's all I got for you for today.